Very good morning. Welcome to the 7th week lecture of Applied Multivariate Statistical Modeling. In this week, we will discuss multivariate analysis of variance. Today, we start with conceptual model. In addition, we give some examples and we see what are the hypotheses and what are the different parameters to be estimated. We also see in the process that what way multivariate analysis of variance is different from analysis of variance. Let us see the next.
Multivariate analysis of variance, which is popularly known as MANOVA. Today's contents are conceptual model for MANOVA, assumptions for MANOVA modeling, estimation of parameters, model adequacy tests, interpretation of results and references. We will see that how much is possible to complete today, and the remaining portion we will be completing in the next class. You see this slide. Last class I have shown you that when L equal to 2, where L stands for number of population and P is 1, then we have used t test, that is the difference between two population mean, that is described through as H0 mu 1 equal to mu 2 and H1 mu 1 not equal to mu 2. And for the p greater than equal to 2 case, that is multivariate case, here also this H0 mu 1 equal to mu 2 and mu 1 not equal to mu 2, but this mu 1 and mu 2 are in the vector domain when p equal to 2, that is the 2 cross 1 vector, and we have used Hotelling t square. Last class I have told you that when L greater than equal to 2, that is 3 or more, for one variable case you will be using ANOVA, and we have discussed one way ANOVA, two way ANOVA, three way ANOVA and multi-way ANOVA concept. Now, if your number of population is more than 2, that is 3 or more, and as well as number of variables are more than 2 or more, in that case what will happen? You will find out that you require to use MANOVA, not ANOVA. So, essentially what we have discussed then, when we will go for ANOVA, ANOVA is you have L number of population, L can be 1 to capital L, that is 1, 2, 3 like this is the L 1, 2, 3, and you will collect ith number of I equal to 1 to dot n number of observations, and you are interested to see the difference in population means, where population is determined by L1, L2 like 1 to L, that is the case. Everywhere the mean value you will find out, here the mean value you will find out, mean 1, we can say x1 bar, x2 bar like this, then finally x bar, that what we have seen last class. Now, in case of ANOVA, that L is greater than equal to 3, that means what you mean to say that if there is 3 or more population with one variable p equal to 1, you are going for ANOVA, and when p L greater than equal to 3, but p is 2 or more, then you will go for MANOVA. And your hypothesis what you will propose we will see later on, but before that let us see one example. This is an example. Last class in ANOVA we have seen that process A, process B, process C producing steel washers with certain quality characteristics, that is outer diameter. So, with one quality variables. Now, here we are adding one more quality variable, that is inner diameter. So, that means the steel washers produced by the three processes are measured in terms of their two quality characteristics, that is outer diameter and inner diameter. So, here P equal to 2, and there are three processes, process A, process B and process C. So, our case example case is capital L equal to 3 and small p equal to 2. So, this is a case for MANOVA. This is a case for MANOVA, what we have discussed here. Okay. I told you in last class also, the one of the useful way of looking into data is the box plot, and if you see the box plot for the two different variables, inner and outer diameter, for the three different processes, process A, process B, process C, you have seen in last class that for outer diameter the mean differences are quite visible from the box plot, and if you see the lower figure where it is the inner diameters are plotted in terms of box and whiskers. So, you find out the mean value for process A, that means the mean inner diameter is this one, mean inner diameter for process B is this, mean inner diameter for process C is this one. So, apparently if we want to say about the differences in means between the three processes, perhaps process A and B means are not different, but process C is different from process A and B. If you see the outer diameter case, here process A and C's mean differences are not significant maybe, but process B it is different from both A and C. So, there are two types of pictures now. From outer diameter point of view, you are saying that, and also we have seen in ANOVA that process B is different than process A and C, but here if we add inner diameter, what is happening here, that process C perhaps will differ in terms of their mean values of inner diameter from A and B. Now, we want to see collectively what is the difference in mean vector, where this vector will be determined by mean diameter for outer diameter as well for mean inner diameter. Okay. So, collectively are the three processes different or not, that is what we will be testing through MANOVA. So, we require certain notations to fully understand the application of ANOVA as well as MANOVA, because in case of MANOVA there is one more more dimension is added, as number of variables will be more than equal to 2. So, P will be greater than equal to 2. So, as a result you see in ANOVA what we have said, we said like this, that ANOVA case here it is number of populations, this axis and this axis is observations, and for different population you have obtained certain observations, and somewhere there is one observation which is XIL, ith observation on the nth population, and it is a scalar quantity. Now, in case of MANOVA what will happen, you will find out that this side is number of observation, let it be population in the same manner, populations, and this side is observation, that is number of observations. Then we will add one more dimension which is number of variables. So, if we denote number of population in terms of L, number of observation in terms of I, and number of variables in terms of J, then what will happen, your general structure will be like this. This is the data structure basically. Getting me? What will happen for any observation? Suppose if I say this is my xil, getting me? This is our xil, then xil is no longer a scalar quantity. In ANOVA this is a scalar quantity, in MANOVA it is not a scalar quantity, because for this cell you see, if I go 1, 2, 3, depending on the number of variables, this xil will have more number of values. So, we can say here that xil is no longer a scalar quantity, it is a vector. What we will write here? xil1, xil2. So, like this xil, how many variables are there? P variables are there, p cross 1. And there is the complexity, because one more dimension is added and your total work is now in 3-dimensional case, it is not a 2-dimensional issue. If this is the case, so this is the general observation. Okay. This is my general observation. As you have p variables, so you also have p mean values. So, now I am writing that the mean vector for population L, there will be p mean values mu L1, mu L2, like this mu LP, p cross 1. And as there are p variables, again there will be one covariance matrix. If I write like this SL sigma L, instead of S we will be writing when we take the sample. Now, we are writing like this, then what will happen? This will also be p cross p matrix, p variables are there. Your L varies from 1 to capital L. So, then there will be sigma 1, sigma 2, like this sigma capital L. So, there will be similarly mu 1, mu 2, mu capital L. For mathematical simplicity, we will be using this term, although this is a vector, basically we will be using this term like this xil without bringing the variable part. Variable part is implicit here, because xil is nothing but this one. This is the general observation. Okay. So, you see this is pictorially given in this figure. I think it is very clear now for all of you that ANOVA, where we have different populations and different observations, and for MANOVA it is not population, observation and variables, and this general observation is xil, which is this one. Okay, you have to keep in mind this vector part. Then MANOVA assume something, and MANOVA do also hypothesis testing like your ANOVA. What are the hypotheses here? What are the hypotheses in ANOVA? You said mu 1 equal to mu 2 equal to mu L, that is your H0, and your H1 is mu L not equal to mu M for at least one pair of mu L mu. One pair of mu means either mu L or mu M. L equal to 1 to capital L, M equal to 1 to capital L, and L not equal to M. And in MANOVA case the same hypothesis is same, that we are saying H0 mu 1 equal to mu 2 equal to mu L. Please keep in mind, by saying this we are saying like this mu 1 1 mu 1 2 like this mu 1 p equal to mu 2 1 mu 2 2 mu 2 p equal to finally mu capital L1 capital L2 capital LP. That is the difference. In ANOVA case it is scalar quantity, MANOVA case it is the vector quantity. And your alternate hypothesis that mu L not equal to mu m, by saying this you are saying that mu L1 mu L2 mu LP this not equal to mu M1 mu M2 for at least one pair of LM. Okay. So, like ANOVA, we will also partition the general observation. So, what is my general observation here? My general observation here is XIL. Let us see in ANOVA case, parallelly see MANOVA case. In ANOVA case, XIL is partitioned like this: mu plus mu L minus mu plus XIL minus mu L. This is the way you partition, and we say this equal to mu plus tau L plus epsilon I L. Mu is grand mean, tau L is the population effect, and we are saying that no model is perfect, it cannot predict exactly same exact value for all the observations, there will be random errors. So, sigma epsilon I L is the random error part. Okay. So, same partitioning possible in MANOVA. What we will write? XIL equal to mu plus mu L minus mu plus XIL minus mu L. So, it is similar, it is like this. We have seen that XIL is XIL1, XIL2, XILP, p variables are there, which is equal to mu 1, mu 2 like our case is mu L, that is the grand mean case, plus if we write like this, I think earlier we have written mu L1 minus mu 1 mu L2 minus mu 2, the same manner you come mu, I think L, this is mu 1, now mu L minus mu. So, all cases L will be there, and then every case what we are doing, this is mu 1, this is mu p, not mu L, this is mu p, please write down this one as mu p. So, then mu L p minus mu p, that is why the problem comes. I have written m L. Then plus same thing xil, all this you write xil 1 minus mu L 1, xil 2 minus mu L 2. Same manner you come xil p minus mu L p. This is what is partitioning the general observation into three components. One is, this one is the general observation, the left hand side, general observation vector, and right hand side this is your grand mean vector. Then other one, that mu L 1 minus mu 1, this one we are saying population effect vector, population effect vector, and last one is random error vector. Okay. So, this partitioning, for this one, this partitioning we can write also in the same manner. Earlier we have written that this first one, this is xil, fine, then second one is mu, that is also fine, then third one is, it will be tau L. Okay, plus epsilon IL. So, this is my general observation, this is my grand mean vector, this is the population effect vector, this is the random error effect. Okay. So, if this is just, we will just explain what I mean to say, that let us write down the tau L case. This will be a vector tau L 1, tau L 2, like this tau L p, p cross 1 vector. So, when we say population, Lth population effect, that is related to all the variables considered. Here we are considering p variables. So, tau L for p variables. Okay. So, if we frame our hypothesis like this, that H0 mu 1 equal to mu 2 equal to mu L, and H1 mu L not equal to mu m for one pair of Lm, then using this tau L concept, you can find out the null hypothesis also. What will be the null hypothesis? What is tau L? Tau L is mu L minus mu. Now, if H0 is true, if this one is true, that means all means are equal, then what will be the grand mean? Grand mean will be n1 mu 1 plus n2 mu 2 plus dot 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 n L mu L divided by n1 plus n2 plus n L. If all means are equal, then what will happen? We can write all mu 1 equal to mu 2 equal to mu L. So, it will be n 1 plus n 2 dot 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 plus n L by n 1 plus n 2 plus n L into mu, because this will be cancelled out. So, what do we mean then? We want to say that every mu will be equal to the grand mu. Getting me? So, then what we can say that mu L equal to mu if H 0 is true, which indicates tau L equal to mu L minus mu equal to 0. That means, we can create null hypothesis like this: tau L equal to 0, L equal to 1 to capital L, and your alternate hypothesis will be tau L not equal to 0 for at least 1 L. So, if you test this hypothesis in terms of mu and the other hypothesis in terms of tau L, you are actually doing the same thing. Okay. So, in MANOVA we will do this in the same manner like ANOVA, partitioning the, now we partitioned the observation. Now, we will see that how to partition the this one, your variability part. But what are the parameters you are estimating in MANOVA? Your parameters will be this tau L, actually mu L also you have to estimate, mu you have to estimate, and you have to estimate also the error terms. And another issue here is, if you go for unequal sample size, then the weighted effect of the population, that sum will become 0, and if you go for equal size, that is again the sum of the effects of the populations will become 0. I think you can prove the second one also. What about first one? Why it is 0? What I mean to say? We are saying that sum total of NL tau L, L equal to 1 to capital L, this is 0. You see, what is tau L? Tau L is mu L minus mu. So, if you write down here sum total of L equal to 1 to capital L N L into mu L minus mu, the LH, that is the left hand side, what you will get here? This one, L equal to 1 to capital L N L and mu L minus L equal to 1 to capital L into mu. So, you have already seen that mu equal to n 1 mu 1 plus n 2 mu 2 plus n L mu L by this. So, that means that sum of this n L mu L can be written like this, can be written as this one can be written like this, this into this. Okay. And then that will be cancelled out, and you will become, it will be N L, here it is N L is there, you have not written this one is okay. So, how it is okay. So, what we mean to say that this quantity is N 1 plus N 2 plus N L into mu, yes or no? And I have told you this, that N 1 plus N 2 plus N L mu equal to N 1 mu 1 plus N 2 mu 2 plus N L mu L. So, again this N 1 mu 1 plus N 2 mu 2 plus N L mu L is this one, N 1 mu 1 plus N 2 mu 2, this is this part, minus N 1 plus N 2 plus N L mu, this quantity equal to this quantity, becomes 0. Problem? You have to understand that the grand mean is mean of the means, weighted case here, n 1 mu 1 plus n 2 mu 2 plus n L mu L by total frequency, and this one is mu. So, you can write from here n 1 mu 1 plus n 2 mu 2 plus n L mu L equal to n 1 plus n 2 plus n L into mu. Then if you make minus, this will become 0. This is the case. Okay. Thank you very much.